Thank you very much. Welcome to all of you. Um, you may on occasion hear loud banging sounds and drilling. I hope it will not distract, but there's some construction taking place out of my window. And it's either that or I hide in the basement, and my basement looks like a bomb shelter. Uh, just to remind you of where let me also again say, feel free to ask questions at any time, either through the chat or in person. I welcome them. Let me remind you of where we are. I have discussed a model where agents have available money and unlimited amounts of it, so there is a medium of exchange. We've also looked at a model where perhaps money was not available, the Staff-Shapley housing model, but agents owned homes, so they had property rights in something, and therefore we could get away with the absence of money by relying on barter. I now want to look at a setting where there is no money and agents do not have property rights over anything. In other words, there is nothing that in principle they can use to barter. Let me give you two examples that you should keep in mind that would capture such a setting. One is allocating office space to faculty, for example. Okay. So this is a typical example of resource allocation within a firm or organization. Typically within an organization, we do not have markets, and typically we do not ask faculty to pay for their offices, but I could imagine in the United States that is not too far away on the distant horizon. And also, we typically do not use money to decide which faculty member gets which office. Sorry, I said that already. And faculty do not have property rights over offices. In other words, you do not have a legal right to an office or any particular office. The second example I want you to have in mind, and it differs from the first example in an important way. In the faculty example, each faculty member is generally interested in no more than one office. There are, of course, exceptions to this rule, but we will ignore that. Okay? The other example involves students interested in getting particular courses. Once again, we typically do not use monetary transfers to decide which courses a student gets. We charge a fee for them to register at the university, but then we do not subsequently say, oh, if you want to get into Martin's very popular market design course, that's an extra 200 euros. And clearly, there is no property right. We do not promise any student that they have a right to a seat in any particular course. Now, the difference between the student example and the faculty example is that the student is interested not necessarily in a single course, but a bundle of courses. Now, I gave you academic environments to illustrate this. Let me conclude actually with a third example to show you that this is not purely an academic problem. Within the United States, the Joint Defense Logistics Agency is responsible for allocating inventory to the various bases of the US military, both within the United States and abroad. And what are they allocating? Well, the obvious thing are bullets, blood, baked beans. Now, they do not have prices to decide who gets what when. And this is important because the supply both of goods is scarce as well as transportation capacity. Because not only must you have the blood, bullet, and baked beans, you must also have the ability to ship them to the various bases. So a problem that the Joint Defense Logistics Agency has is how to prioritize who gets what and when. The way it is typically done is that the various bases send a message upstream to the, if you like, the planner, saying, we urgently need X, Y, and Z. It's a priority. There is a committee that then evaluates these priorities and then determines who's going to get what when. You can now see the obvious difficulty that they face. Everything is a priority. How do you decide who gets what when? Okay. And because they do not have a transparent way of deciding who gets what when and where and how priority disputes are resolved, agents strategize. And strategizing involves, as you might imagine, over-ordering and hoarding. The classic example of over-ordering and hoarding is toilet paper. My understanding is, in the absence of toilet paper, the US military will grind to a halt. It is well known when Navy ships return from extended cruises and they have to be cleaned out, the cupboards are stuffed with toilet paper. That's because people are worried about not having enough toilet paper, and so they overorder. And as a result, there is a huge amount of toilet paper in the system. Okay. So again, this is an example of an organization that has to make internal resource allocation decisions. They do not have access to money because we typically would not expect the various bases and divisions to pay for priority, because that raises the question of where does the money come from? And there is no clear notion of property rights. In other words, in what sense is it that I have a right to a particular product or service at a particular time? Okay. Is everyone clear about the kinds of problems then that I'm interested in? Okay, so I'm going to begin with the simple case of every agent interested in consuming at most one object. This is the case of assigning officers to faculty. You're assigning an indivisible good, potentially. And here I'd like to remind you of something. As I said, I hope the drilling is not distracting. So here I want to remind you of something that one of my advisors, Peyton Young, is fond of saying. Everything is divisible for a price. Okay? And that's a lesson we learned from Solomon and the baby. And so when we say you have to allocate something that is indivisible, you really should not fall into the trap of thinking that it is impossible to divide the object. It is possible to divide the object, but it may come at a huge cost. So the right way to think about things is that we want to divide what is ostensibly indivisible, but we want to divide it in a relatively low-cost way. And within economics, the dominant, if you like, the dominant point of view is that a low-cost way to divide an indivisible object is through lotteries or randomization. And you can interpret lotteries or randomization in two ways. One is literally there is a lottery and the lottery determines whether you get the object or not. The second is that you can interpret a lottery or probabilities as a form of timeshare, meaning for a fixed time period, I get ownership or possession of the object for a fraction of the period. Does that make sense? Okay, there are three main methods for allocating indivisible goods when agents have unit demand. Okay. As I said before, they involve randomization, and the randomization is determined by choosing what are known as probability shares in the good. So I promise you a 20% probability in good one a 15% probability in good 2, a 17% probability in good 3, and so on. Okay? Those are the probability shares. Okay? Now, the technical problem is I can make these promises, but are these promises feasible? In other words, is there indeed a lottery over the possible allocations of the goods to the agents so that you indeed get a 20% chance at good 1 and a 17% chance at good 3, and so on? Okay. Now, this is a particularly important point, and so I'm going to pause here in case there are questions, particularly about whether I've explained myself properly on this point. Okay, if not, let me formalize. N is the set of agents, M is the set of indivisible goods, Sj is the number of available copies of good J. In the allocating offices to faculty, Sj would be 1 and J would be the label of an office. Xij is the probability with which an agent I in N will receive good J. The basic constraints that we would impose on the probability shares are the ones that you've seen before many times, at least in my presentation on Monday. Sum of the Xij's is less than or equal to 1. In other words, the total probability that is allocated to an office is at most 1, and then, is at most Sj, and the total probability of an agent receiving a good is at most 1. And the Xij's are between 0 and 1. Now, we know that the constraint matrix here is totally unimodular, which means that all of the extreme points are integral. Why is that important? If I pick anything in the interior of this polytope, I can write it as a convex combination of the extreme points. So let me write that out, which is X can be written as a convex combination of the extreme points, which I will label as E superscript J. Now, in the case when we are allocating offices, so there is only one office of each type, what is an extreme point? An extreme point is a permutation. It's an assignment of agents to offices such that each agent is assigned to at most one office, and each office is assigned to at most one agent. What is a convex combination? It is simply a collection of non-negative numbers that add up to 1. In other words, a convex combination is really a lottery over the extreme points. So that means as long as my promises live in this polyhedron, I can implement it as a lottery over permutations. So when I promised Charlotte, for example, a 20% chance at office number 1 and a 40% chance at office number 2, and I promise, let's say, Jake, an 80% chance at office number 1 and a 60% chance at office number 2. Because everything in every row and column adds up to 1, I can indeed feasibly find a lottery that satisfies those promises. Now, in the case of 2 agents and 2 objects, this is easy to see. It's not so obvious when we move to 3 agents and 3 objects, but that's the beauty of this, of the total unimodularity condition. Any questions so far? So when we're allocating indivisible goods and each agent is interested in consuming at most 1 unit of each good, that there's a way to do this easily, which is I pick my favorite point in the interior or anywhere in the assignment polytope, and any such point can be implemented as a lottery over permutations. And so it is now a matter of deciding what is my favorite point in the assignment polytope. Okay. Here is a more complicated example to convince you of why finding a lottery is non-trivial. In that table, I have shown you the promises that I have made to four agents, agents 1, 2, 3, and 4. And 4 goods. So notice I have promised agent 1 a 50% chance at good A, a 0% chance at good B, a 50% chance at good C, a 0% chance at good D, and so on. Now, in the absence of that result about the extreme points of the assignment polytope being integral, if I were to ask you, look at these promises, is there a feasible way that I can implement them? Well, you might say, oh, this is easy enough in this example. Take good A and just flip a coin to decide whether or not to give it to agent 1 or 2. Take good B, flip a coin and decide whether to give it to agents 3 or 4. Take good C, do the same thing with respect to agents 1 and 2, and with good D, do the same thing. Make sense? That fractional allocation can be represented as a 50-50 combination of the following. There's a 50% chance of choosing the permutation that you see at the top, 50% chance of choosing the permutation you see at the bottom. Right? So I can describe my lottery as, rather than a sequence of coin flips where I get together groups of agents, I simply say, here are the set of possible ways of assigning all offices to all agents, and I'm going to pick each of these assignments with a certain probability. Okay, now, there are 3 basic methods that have been used to find these lotteries. The first is known as serial dictatorship. Each agent is assumed to have a strict preference ordering over the objects. The planner selects a permutation of the agents. Agents are selected in that order to pick their most preferred object from among the ones that remain. The planner is free to choose that permutation in any way they like. In some applications, that permutation is chosen uniformly at random, in which case this mechanism is called random serial dictatorship. Of the 3 mechanisms that I'm going to describe for allocating indivisible goods in the absence of money and property rights, this is by far perhaps the most popular, and this is basically the one that has the most documented instances of being used. What are its virtues? It is simple. It is clearly a dominant strategy for agents to truthfully report their preferences. And of course, it produces an outcome that is Pareto optimal. One example of where such a mechanism was used was both in my department to allocate new offices to faculty when we moved to a new building, and also earlier in the Department of Economics at Arizona State, probably about 15 years ago. Did we implement serial dictatorship as described? The answer is no. Rank hath its privileges. So faculty were divided into 3 groups: assistant, associate, and full. Within each group, there was randomization. Now, if you implement in such a high stakes situation, there is a concern that perhaps it will not be implemented in the way that it was proposed. So names were written down on slips of paper. We all gathered in a room. The department administrator selected the slips of paper from a bowl. One word of advice: be sure to check that everyone's name appears on a slip of paper. In our case, 3 faculty members were inadvertently left off. After the selections were made, and now a delicate issue arises. A selection was made. I was given an office. It's a very nice office. Do I have a property right over that office? And what about my 3 colleagues whose names were inadvertently left off? How do we handle that? Should we put everyone's name back in the pot and repeat the procedure? One argument is, of course, that's the right thing to do. Naturally, those who have very nice offices resisted. Luckily, our chair had set aside some offices for the use of visiting faculty, which were relatively attractive. And so the 3 colleagues whose names had been inadvertently left off enjoyed a windfall. They got offices that they were unlikely to have received had their names been entered into the drawing. Now, should we be happy with this particular mechanism? Well, not entirely. And the reason is there's a mismatch between the preference information that we are soliciting from the individuals. We are only asking them for a strict preference ordering over the offices or the objects. Yet we are choosing a lottery to decide what they get. Now, what's the mismatch? Well, if I'm using a lottery, then what I really want is your preferences over lotteries. In other words, how do you feel about a 50-50 chance at Office 1 and 2 versus a 75-25% chance over Office 1 and 2? This is what I mean. So this is why one might be unhappy with this particular mechanism, because important preference information is being thrown away. And how might that important preference information be relevant? Well, once the ordering is selected, but before we choose our officers, you and I might be willing to trade where we appear in the ordering, because trading effectively involves an exchange of lottery tickets. And depending on how risk averse or risk seeking you and I are, there could be a potential beneficial exchange of lottery tickets. Does that make sense? So in this larger space of preferences, the outcome that we get from random serial dictatorship may not be Pareto optimal. Okay, so this is a reason why one might be unhappy with serial dictatorship. Okay? Now, there are variations. Another thing you now might ask is, I understand how serial dictatorship works when each agent is interested in consuming a single object. How would this work when agents are interested in consuming multiple objects? Think, for example, now about the students choosing courses. One variation you could imagine is there's an ordering of the students. The first student chooses their most preferred subset of courses as long as there is available supply. And then so on down the list. But that is not the only variation you can imagine. Here is another variation that used to be implemented at the Harvard Business School. The first student in the list chooses a single course. Then you go down the list all the way to the last student. And then you start another round, but you begin with the last student and go all the way back up the list. So you are oscillating up and down the list. Now, that results in a different lottery than the one where each student gets to pick their favorite set of objects when it is their turn to pick. So I mention this to point out that if you attempt to generalize these mechanisms to the case where agents are interested in consuming more than one object, it is not obvious what the natural or appropriate generalization should be. Okay. If you are unhappy with serial dictatorship, Bogle, Manaya, and Moulin proposed a very nice mechanism which makes use of some of the preferences that agents have over lotteries. And so in a certain sense, it delivers outcomes that may be more desirable than random serial dictatorship. As I know of no documented instance yet of where this mechanism has been used, but it is such a charming mechanism that one cannot help but pay attention to it. So let me describe the mechanism and then outline some of its properties. Again, you assume that agents have a strict preference ordering over the objects. And now what you do is you ask the agents to start eating their most favorite object at the same speed. Now, what do I mean by that? Well, let's look at an example. Do I even have one? Let me make one up. So let's suppose, for the sake of argument, we have 3 agents. Let me call them 1, 2, and 3. And let's suppose agent 1's preference ordering is as follows. These are their preference orderings. Now we ask each agent to consume their favorite object at the same speed. And this happens until one object runs out. So in this example, agents 1 and 2 will start eating object A, and agent 3 will eat object B. After a half unit of time, object A will become exhausted. At this point, agents 1, 2, and 3 agent 1 has consumed half a share of object A, agent 2 has consumed half a share of object A, and agent 3 so far has consumed half a share of object B. Okay, because I said they consume until one object runs out. Object A has now run out. We removed object A from the list. We now ask the agents to start consuming their favorite object from among those that are left. Now what will happen? Agent 1 will start consuming object B. Agent 3 will continue to consume object B, But now there is only half a unit of object B left. So if they consume at constant speed, eventually object B will be exhausted. And when it is exhausted, agent 3, sorry, I made a mistake here. Agent 3 will end up with an additional 1/4 of object B, and agent 1 will end up with 1/4 of object B. Agreed? Object B is exhausted. Now, agent 2 at the same time was consuming object C without any competition from anyone else. So agent 2 will at this point in the clock have consumed 1/4 of a unit of object C. We then ask the agents, now start consuming your favorite object from among those that remain. Well, object A is exhausted, which means they are now all consuming object C. There is 3/4 of a unit of object C remaining. 3 people consuming, that means they will each end up with 3/8. But agent 2 will end up with an additional 3/8 because they got 1/4 of object C from an earlier time period. Is it clear how the mechanism works? Now notice, I built a table that records the probability shares that each agent is entitled to. So I am promising Mr. 1 a 50% chance at object A, a 25% chance at object B, and a 3/8 chance at object C. Now, can I feasibly promise him that? The answer is yes. The entries in that matrix are a feasible solution to the assignment problem. The rows and the columns sum to 1, provided I've done my arithmetic correctly. And therefore, I can express those probability shares as a lottery over deterministic allocations. Jake, I think you spotted a mistake. Is that correct? Okay, so tell me what my mistake was. Should be 3/4 left of which good? Actually, why don't you just pipe in rather than type? Oh, they each get 1/4.
Sorry, I had to connect my microphone, so it wasn't going.
All right,
so it should be, if player 2 consumed 1/4 of good C, I would expect there to be 3/4 left, right? So each gets 1/4. Yeah.
So this should be 1/4 plus 1/4 plus 1/4. Thank you. Okay, good. Now the rows and the columns add up to 1. So there exists a way to implement these promised probability shares as a lottery over
microphone for you, sir.
Say again. Okay. Any questions? Okay. That's the probabilistic serial mechanism. Why should you prefer it to random serial dictatorship? Well, the answer is because it satisfies a stronger efficiency condition than random serial dictatorship does. This efficiency condition is called ordinal efficiency. And so in some sense, it takes into account preferences that agents have over lotteries, which random serial dictatorship doesn't. What's the drawback? The drawback is probabilistic. It is not a dominant strategy for the agents to truthfully report their preferences. Why is that? Well, imagine your most preferred object is extremely popular. If you start consuming your most preferred object, you may end up with a tiny amount of it. So you might say, you know what, let me skip my most preferred object and go down to something that's lower in my preference ordering, but currently nobody else is consuming, so I can get a huge amount of it. So basically, agents face a trade-off. I can get tiny amounts of my most preferred object versus a gargantuan amount of my less preferred object. And that potentially might leave me better off. And for that reason, I may have an incentive to misreport my preferences. Okay. The response to this is, yes, this is certainly true. But if you have a large number of agents, then your ability to gain by this kind of misreporting is in a precise sense very small. So one can argue that in a large economy with a large number of agents, one shouldn't be concerned with this kind of misreporting because the benefits will be extremely small, so it reduces the incentives for agents to engage in that kind of strategizing. As I've said, I'm unaware of any documented application of this particular mechanism. And once again, if you think about moving from agents interested in consuming at most one object to multiple objects, it is not immediately clear how you generalize this mechanism. And importantly, this notion of ordinal efficiency that I referred to, it's well defined when agents are interested in consuming a single object. It is not well defined when agents are interested in consuming bundles. So what is also up for grabs is how you should define efficiency when you move to agents interested in consuming bundles as opposed to individual objects. Any questions about probabilistic serial? Third method is called competitive equilibrium with equal outcomes. This makes explicit use of agents' preferences over lotteries. So it assumes that agents' preferences can be represented by a von Neumann-Morgenstern utility function. Okay. Here is how it works. You're going to create a pseudo market where you give individuals artificial currency, and typically you give them all the same amount of artificial currency called their budget. And you can just assume that everyone gets a budget of $1 or whatever is your favorite term for artificial currency. Okay. Now, what the agents are going to be trading is probability shares. So what they are going to be buying and selling is the probability of receiving a particular good. And the easiest way to convey this is to describe what is an agent's choice problem when you announce prices. So you, the planner, will announce a price for object J. Given those prices, agents are supposed to tell you what fraction of object J they wish to consume in order to maximize their utility subject to their budget constraint. That fraction of object J we interpret as a probability share. So if BI is the budget of agent I, notice I am not requiring that agents have the same budget. I simply said in that some applications you give all agents the same budget. You don't have to. How does an agent determine what shares she is willing to buy at the announced prices? Well, Xij is the fraction of good J, or the probability share in good J that agent I consumes. If she consumes that, she has to pay a price of PJ per unit. Therefore, the probability shares that she chooses cannot exceed her budget. And because they're probability shares, the total amount that she consumes has to add up to at most 1. Notice less than or equal to 1, which is I'm allowing the agent to say, I don't like what you're offering. I don't want anything. And she chooses these Xijs to maximize her expected utility. Or equivalently, I'm assuming that her utility is linear in the fractional quantities of these indivisible goods. So this is the agent's consumer choice problem. It is a straightforward linear program. Okay. It's easy enough to solve. Okay. The solution to this program determines each agent's choice correspondence. In other words, the set of lotteries that she is willing to purchase at price P. Okay. That's a convex set. The set of optimal solutions to a linear program is a convex set. It's a convex set. It's, of course, closed. Set of optimal solutions to a linear program is a closed set. Okay. So every agent can give me their choice correspondence. And now what I look for is an element, which I'm going to call Xj, in every agent's choice correspondence. That element will, of course, depend upon the price that I've announced. And I want to choose a price so that the market clears. If I give everyone the same budget, I would have chosen a competitive equilibrium outcome with equal incomes. Okay. Now, this is clearly a more complicated procedure than the other two that I've described. Why? You have to find a fixed point, right? Because I'm finding a competitive equilibrium. Now, some of you may say, wait. Utilities are linear in quantity. Isn't there an old result of Bernard Cornet that says in economies where utilities are linear in quantities, competitive equilibria can be determined via convex programs? That is true. However, there's a catch. It's the presence of this constraint. Okay? We're putting a cap on how much an agent can consume. So Cornet's result about competitive equilibria does not apply. Cornet's result applies when this constraint is missing. Okay. So exchange economies where utilities are linear in quantity can be formulated, finding competitive equilibria in such economies can be formulated as a convex program. This is indeed an exchange economy, but utilities are not linear in quantities because of this capacity constraint that says the total probability shares you consume is at most 1. That essentially makes utilities piecewise linear in the quantities consumed. Okay? And it's actually an open question whether you can write down a convex program to solve this, to find the competitive equilibrium. I think the jury leads towards no. There is a recent paper that suggests that's the case. But nevertheless, it just seems like such a simple problem that maybe there is a reasonably fast algorithm for finding competitive equilibria. And I believe there is a recent paper by Vijay Vazarami at least suggesting a fast approximation algorithm for solving this. But I don't remember the exact statement of the result off the top of my head. And so for that, I apologize. Okay, it's a more difficult problem to solve. Is there a reason that you should prefer it to the other two methods? The answer is yes. One, because you're getting a competitive equilibrium, all competitive equilibria are Pareto optimal, but this is Pareto optimal with respect to the von Neumann-Morgenstern preferences. So it is satisfying a stronger efficiency property than the previous two mechanisms. In addition, it also satisfies a desirable fairness property if you give everyone the same budget. And that fairness property is envy freeness, meaning the lottery that I get, I prefer to the lottery that you get. Notice I didn't say I prefer the object I get to the object that you get. I prefer the lottery that I get to the lottery that you get. Finally, the solution to this, because supply must meet demand, must live inside the assignment polyhedron, and therefore any fractional solution to the competitive equilibrium can be implemented as a lottery over deterministic integral allocations. Okay. What's the drawback of this mechanism? It is not a dominant strategy for the agents to truthfully report their preferences. We have competitive equilibrium. That means we're relying on the price-taking assumption, meaning we're assuming when agents give us their choice correspondences, they're not strategizing in any way. What's the counter argument? If your economy is large enough, no single agent can influence the price significantly by misreporting their preferences. Now, this poses something of a problem. In the example of allocating office spaces, that's an assumption that is simply untenable. We do not have a large economy. And strategizing is probably relatively easy because agents have a good idea about each other's preferences. Okay? And the second issue is agents' preferences are probably not over individual offices, but over who else is getting the neighboring office. Okay? And in both the Arizona State and the University of Pennsylvania example that I gave you, faculty members engaged in some coordination ahead of time about which offices they would pick so that certain clusters of individuals could be together. Okay. And this is not taken into account in these kinds of mechanisms. Okay. The only mechanism that is robust to all this other kinds of strategizing is serial dictatorship. Okay. And that's because it essentially ignores any information you give it about preferences. Okay. Right? It chooses the order, that's it. And it chooses the order without any knowledge of the preferences. As with the other two, when you think about moving from allocating objects to agents who are interested in consuming a single good to a setting where agents are interested in consuming bundles of goods, it is not obvious what the generalization of competitive equilibrium with equal incomes should be. So now what I want to do is actually to think about settings where you're allocating bundles of goods. And the basic problem we're going to face is the following. It's a problem that I mentioned earlier when you're allocating bundles of goods. So let me remind you of what it is. Let M be the set of goods, N be the set of agents. I could define Xi of S to be the probability that I gets the bundle of goods S. Now, what constraints would I impose? The total probability of getting a bundle should not exceed 1. What else would I impose? I would impose this. I'm assuming 1 copy of good J. And of course, I would impose this. What's this constraint that I wrote down? Well, it simply captures the fact that if I look at good 1, all of the promised probabilities have to add up to at most 1. Oh, sorry, Martin, I missed your question. You said, isn't it a lot to ask for card? Actually, I'm very glad that you asked that question, because it is a point I wanted to discuss. So Martin's question was, surely another critique of competitive equilibrium with equal incomes is that you're asking agents for their von Neumann Morgenstern utilities. Right? Yes, and in fact, when you move from allocating an individual good, when you move from agents consuming an individual good to consuming a bundle, this problem is going to get even more pronounced because you're asking agents to give you their preference ordering over lotteries, not over whether I get office 1, 2, 3, or 4, or 5, but whether over I get bundle A, bundle B, bundle C, bundle D. In other words, 2 to the cardinality of M entities. Okay. This is indeed a huge problem, and I intend to discuss it a little bit more because we happen to have an authority on this subject, who is Martin, and I'm going to delay it when I get to the application of allocating courses to students, okay? And I'm going to do that in a moment. But now let's think about the problem of allocating bundles rather than individual objects. If I follow what we did with unit demand, I would define the variable xi of s, the probability share in bundle s. My xi of s's obviously have to satisfy those constraints. But what is the catch? As we saw on Monday, the extreme points of this system of inequalities are not integral. Therefore, if you come to me with a list of promises that are encoded by xi of s, there is I cannot guarantee that there exists some lottery out there that will deliver on those promises. And that's because of a failure of integrality. And there's no way around this. If you want to work with probability shares, because they're convenient to describe, oh, you get a 20% chance at object 5, oh, you get a 30% chance at this pair. They're easy to describe and easy to interpret. But a particular profile of probability shares does not always map to a lottery over allocations. And that happens because of the failure of integrality. There is no way around this problem unless you are willing to approximate. Now, this raises the question of how you should, if we approximate, what is it that we are approximating? As you can imagine, there are papers that propose different notions of approximation. I really don't have the time nor the inclination to survey all of the different proposals. I want to highlight that what is an appropriate notion of an approximation is something that is up for debate. I am going to focus on a very particular notion of approximation, which involves burning some of the supply. In other words, withdrawing some of the objects that are available to be allocated. So this would mean removing some of the offices from consideration. This would mean intentionally reducing the capacity in some classrooms. This is why I call it burning, because this involves a definite loss in utility, because I am removing things that are valuable. But this echoes the point I made earlier. Everything is divisible for a price. And the price that I am willing to pay is that I will burn up some of my resources. And now the question is, how much am I having to burn up? Now, to convince you that I can produce a fair allocation by burning enough stuff up, let me burn every single office. No one gets anything. This is clearly fair. It is clearly a dominant strategy for you to truthfully report your incentives. And given I've burnt it up, there is no other allocation that can do better. Now, I purposely picked an extreme example to highlight the fact that if I'm prepared to be wasteful, I can achieve many other desirable objectives. Okay. The goal then is to figure out, is there a way to be parsimonious when you're being wasteful and achieve these desirable objectives? Everyone with me? So my focus is now going to shift to approximation. And I'm interested, I said, in a particular kind of approximation, and I'm going to describe that formally. So we live in a world where there is some supply of each good represented by a vector little b. And now all of the mechanisms that I've described to you and all of the mechanisms that have not yet been described can all actually be represented in the same way. Agents give me information, and based on that information, I give the agent what's called a budget or an option set, meaning given the information that you have told me about your preferences, given the information that other people have told me about their preferences, I have constructed the following set of items that you may choose from. That set of items is called your budget or your option set. In the competitive equilibrium with equal incomes, that budget set was described by a vector of prices. I didn't actually physically hand you the set. I gave you an indirect description of it, which is I gave you an income and I gave you prices, and I said you can choose anything that you can afford. In random serial dictatorship, your budget set is the set of objects that are left over after the people in front of you have chosen. Okay? So this budget set that I give to you, it can be constructed in all sorts of elaborate and complicated ways. I don't care how. At the end of the day, I can describe all mechanisms in terms of a mapping from information you give me to budget sets that I give you. I give you the budget set. Then what do you do? Well, the budget set is the list of items on the menu that you are allowed to choose from. So you will choose your most preferred element in the budget set. That need not be unique. So I'm going to call that S superscript J. That's the set of your most preferred items in your budget set. My goal as the planner, in part, is to ensure feasibility, that you end up choosing something from your budget set that I can feasibly deliver on. In other words, I have to design these budget sets using the information that you gave me about your preferences so that your demands add up to the available supply. Does this make sense? Okay. By framing the problem that way, I can make use of this wonderful lemma of Shapley, Folkman, and Starr. The lemma was actually developed by Shapley and Folkman. Folkman was a mathematician who died very young, and this collaboration, I believe, occurred while Folkman was still in hospital suffering from cancer. It was never published. The proof appears in correspondence between Lloyd Shapley and Folkman himself. Starr stumbled upon it and found a use for it. And this is the reason it's called the Shapley-Folkman-Starr lemma in economics. In mathematics, it's simply referred to as the Shapley-Folkman lemma. There is an entire literature that grew out of this lemma, which can roughly be summarized as saying the Shapley-Folkman-Starr lemma is an analog of the central limit theorem for sets. So what does the central limit theorem say? Average of a large number of independent random variables is approximately normal. One version of the Shapley-Folkman-Starr lemma is that the average of the Minkowski sum of a large number of sets is approximately convex. Let me state two versions of the lemma. Okay? You can get from one to the other, but it's useful to have both in mind. Okay? I have a collection of sets SI, and I'm going to look at the Minkowski sum of the convex hull of them. Notice that is the same as looking at the convex hull of the Minkowski sum. So what is the Minkowski sum of a set? Well, if I have two sets, here's A and B. I should have done it that way. The Minkowski sum of A and B is the set that you construct using the following recipe. Pick a point in A, call it X, pick a point in Y, call it B, add them together, and put that in the set A plus B. Go back in, pick another point X prime, pick another point Y prime, add them together, put them in the set A plus B. So literally the Minkowski sum is take something in A, add it to everything in B, take something in B, add it to everything in A, repeat. So I have a collection of sets. I'm going to look at them and I'm going to pick a vector B that is in the convex hull of the Minkowski sum of those sets. And the claim is the following. There exist xj's in Sj. Notice this doesn't say convex hull of Sj. In Sj, such that, it should be B here, such that the L2 norm between B and these objects is in some sense small, where D is the diameter of each of these sets. What on earth does this have to do with what I just described? Take these sets Sj to be the budget sets of the agents. No, not the budget set, but their most preferred objects in the budget set. Right? So just to remind you, I allow the agent to choose anything in here. The agent comes back and picks out a set Sj of their most preferred items, because they could be ties. These Sjs are the sets that live here. So I'm looking at the convex hull of your most preferred item, most preferred objects, most preferred bundles. What is the vector B? The vector B corresponds to the vector of supplies. What is this condition saying? It's saying, if you allowed me to randomize over your favorite choices, then I could make supply meet demand. So if I could give you fractional amounts of your favorite bundle, so maybe your favorite bundles are bundle number 1, bundle number 3, bundle number 5. Well, I'll give you 1/4 of bundle number 1, 1/2 of bundle number 3, 1/4 of bundle number 5. Okay? That's what it would mean to be in the convex hull. Okay? And I can choose those fractions so that they add up to the available supply. So in other words, I have a fractional allocation that I could give out. But because I don't have divisible objects, I can't hand out half a bundle. Okay? What does Shapley-Folkman star tell me? It tells me not a problem. Because the vector of supplies lives in the convex hull of the Minkowski sum, I can find a bundle to give to every agent J from their most preferred set that is not too, so that the total amount that you give away is not too far from the available supply. So I can hand out indivisible goods, I can hand out bundles, but the catch is there's going to be a discrepancy with what you have and what you give out. My claim is the discrepancy in some sense is small, as measured by L2 norm. So if you think of these as the demands and this is the supply, I am saying that somehow I can find a way that the L2 distance between the supply vector and the demand aggregate demand vector is small. That's one version of the lemma that bounds this discrepancy in terms of the diameter of these sets Sj. Here is a second version. It says every vector B that lives in the Minkowski sum, in the convex hull of the Minkowski sum, can be expressed as a sum of vectors xj, where each xj lives in the convex hull of the sj's. Well, that's not surprising because B lives in the sum of the convex hulls anyway. What is surprising is this condition, that roughly for a large number of those, I can actually choose xj to be in Sj, not just the convex hull. For this lemma to have bite, I need many more sets than I have dimensions. Let me pause here to make sure everyone understands what the lemma is saying. I'm going to use the second version of the lemma because I find this one more useful than the other one. And if there's time, I'll talk about reasons why you might prefer one version of the lemma over the other. But I want to give you an application which I hope will convey how this lemma is being used. straight integer programming application. You can assign an interpretation to this in terms of, I have a bunch of bundles that I wish to allocate to agents. So A is a 0-1 matrix, M rows, N columns. B is the vector of right-hand sides, and I have many more columns than I have rows. I want you to think of each column as, say, representing an agent. And therefore, the entries in a column, which are a 0-1 vector, represent a set of objects that you wish to give to that agent. So since I have the matrix A, feasibility is this. I either give agent J their bundle or I don't. Right? I have a vector B of goods, B1 units of good 1, B2 units of good 2, B3 units of good 3. I have a set of agents. Each agent demands some particular subset of goods. That demand can be encoded by a 0-1 vector that is one of the columns in A. And one question I might ask is there a way to feasibly allocate the goods that I have so that either an agent doesn't receive the bundle that they want or an agent does? So in other words, I am asking for a solution to the following linear integer program. Now, we know that a solution is not guaranteed to exist. And furthermore, even if it did exist, we have no polynomial time algorithm to find it. Now, I'm interested in the cases where a solution may not exist. If it doesn't exist, is there something that I can think of as an approximate solution? Well, let me tell you what the Shapley-Folkman lemma tells me. It says that they can give me an integer solution y star 0-1 such that the L infinity norm between A y star and B is bounded by N. In other words, they will give me a solution where good by good, I will be off by no more than N. Now, is M a big number or a small number? That's going to depend on the size of B. If we're in an economy where there is a huge supply of goods and M is small, now M is the number of rows in A, that would basically mean agents want bundles that are relatively small compared to the number of available goods, in which case I might be willing to live with such an approximation. Does that make sense? Now, how do we get that result? Well, let's define a set S superscript J that consists of two elements, the jth column in matrix A and the 0 vector. Any convex combination of the two elements in Sj corresponds to Xj being fractional. Does that make sense? If I set Xj equal to a half, meaning I'm giving you half of your bundle, that's equivalent to randomizing 50% 0, 50% giving you the entire bundle. Okay. Now, suppose you told me that there was a feasible fractional solution to this system. Let's call it X star. What would that mean? It would mean that I can write B as the weighted sum of the columns of the A matrix. But each of these X star J's is between 0 and 1 because I picked a fractional solution to the integer program. That means B lies in the convex hull of the Minkowski sum of the SJs. Well, now I invoke Shapley-Folkman star. It says that if you have a vector B that lies in the Minkowski sum, you can write it as a sum of vectors, each of the vectors lying in the Minkowski sum, obvious, but you can choose a large number of them so that they actually live in the sets Sj rather than their convex hull, which in this application means I can choose a large number of those xj's to actually be 0 or 1. Meaning I will give you a representation of B with a small number of fractional entries. How many fractional entries? M. That's this. Well, take those fractional entries and round them up to 1. What's my error? At most n. Now, you can look at this and say, I'm not so happy with this. What if m is a large number? You're right. It's not a useful result. Okay. Why is the bound ostensibly so weak? Well, because you are imposing no conditions whatsoever on the A matrix. This is such a general result. There is no condition imposed on the sets S. That's the price you have for the generality. However, if you are prepared to make restrictions on the set S or the matrix A, you can considerably sharpen these bounds. So in other words, there is a line of investigation of Shapley-Folkman-Starr, which involves restricting the sets in appropriate ways in order to get sharper bounds. And those restrictions arise in economic applications for a variety of reasons. And one of them has to do with the fact that the size of the bundles that agents wish to consume can be limited in some way. In the course allocation application, for example, in any particular academic term, no student is interested in consuming a bundle of more than 4 or 5 courses. Now, I don't have time to go through the proof of the lemma. Let me just give you a flavor of one of the kinds of results that you could get, and then talk about course allocation, and in order to rope Martin into the discussion. So here is an example of the kind of result that you could have. You impose a restriction on the preferences of the agents. For the purposes of time, let's suppose the restriction is no agent is interested in consuming a bundle of size more than delta. So in the course allocation application, delta might be 4 or 5. What is the result? Using a variation of Shapley-Folkman-Starr, it says that I can find a perturbation of the original supply vector S prime. So what would my supply vector S represent? The number of available seats in each course. S prime is a perturbation. I remove some of the seats from a course. Okay. I can find a perturbation so that good by good, course by course, the difference between the original supply and the perturbed supply does not exceed delta minus 1. Well, if delta is at most 4 or 5, this quantity is at most 3 or 4. Okay. And what's the conclusion? I can find an exact competitive equilibrium with respect to the S prime. In other words, I may not find a competitive equilibrium with indivisible goods for the supply vector that you give me, but there is an exact competitive equilibrium in a neighborhood of that supply vector. Now, how might this be relevant in terms of the course allocation application? Agents have preferences over bundles of size, let's say 5. They're not interested in consuming larger bundles. I go into each classroom and I remove 4 seats. So if the capacity of the classroom is 50, in my software, on all my schedules, the capacity is 45 or 46. I am guaranteed to find a competitive equilibrium, because if I don't have enough space, I've left, remember, from each room, I've removed up to 4 seats. I can always hand them back in and satisfy the demand. But I may not hand back in all the seats, so I'm burning up value. Is the amount of value that I'm burning up huge? I would argue in many course scheduling applications, not. Why? If a typical class is of size 50, I'm basically burning up 4 seats. But given that not all students turn up at the same time anyway, at least in the United States, and that is only in the first class and the last class, I can probably get away with burning less than 4 seats. So I'm basically burning 3 seats, and I would argue that's not a huge amount. Now, what is the real issue with allocating courses to students? The first is something that Martin mentioned in his question, which is to apply these methods, you're going to have to collect preference information. I need your preferences of the bundles of size 4 and 5. There are a large number of such bundles. As a practical matter, you're never going to get anyone to sit down and tell you what their utility is for every possible bundle of size up to 4 or 5. You are going to have to help them communicate your preferences to them, which means you're going to have to design software that enables them to both think about their preferences and communicate them. And that means you may also wish to limit the flexibility, the language that they use to communicate those preferences. And so that introduces another trade-off. If you limit the language that they use to communicate their preferences, they cannot truthfully communicate their preferences to you anymore. So how do you evaluate the welfare of the allocations that you're producing? You don't actually know their preferences. A second issue is the design of the property right itself. There is another way to think about allocating courses to students. At least in the US, and particularly business schools where these kinds of methods have been used, but not outside of them, rarely, I think. And there are only a small number of classes that are actually rationed. So there are a small number of classes taught by extremely popular faculty members. So popular that in the students' applications to these schools, they often say, well, I want to come because I want to take a class from X. And if they don't get to take a class from X, they will say, I did not have the full fill in the name of business school experience. The reason I mention this is because many classes are actually undersubscribed. So there are only a tiny number of classes that are actually rationed. If that's the case, there's another way to think about what the issue is, which is maybe the product that we're delivering is not courses, but experiences. And therefore the property right is over the experience, and the experience is I must have the opportunity to take a class from X1 or X2 or X3, or let's say up to X4. Well, if that's what the students are concerned with, then here's an alternative design. Every student, when they enter, gets a ticket that gives them an unconditional right to take a class from one member of X1, X2, X3, X4. That's it. The students are free to trade that right among themselves. But every student receives a claim on the small set of professors that are considered to be offering the fill in the name of business school experience. My point is, you can't think about designing markets without also thinking carefully about what is the property right that you are allocating. Now, Martin has actually been involved in the design of a course allocation scheme for at least the computer science school in the Technical University of Munich. So this is an example of course allocation outside of the business school. It is a different environment than the usual business school environment. Within a business school, students are relatively homogeneous. Within the computer science school at the Technical University of Munich, they are not. There's a greater deal of heterogeneity. And another important feature is I think, where students live. In the US, students are typically living very close or on campus. This is, of course, not true in Germany and other parts of Europe, where residential universities are not the norm. And that means their preferences in some ways are very different. It is more about putting together the right schedule than getting the right professor. But Martin, I'm sure, will say more about these matters. So let me end here and take questions if there are any. I'm also happy to take that in the chat. Go ahead, Martin.
Yeah, I have a question regarding the open question you talked about for the competitive equilibrium with equal incomes. Mm-hmm. If I take these optimization problems that you wrote down, I have one for each agent.
You have one for each agent, correct?
And I have these equilibrating conditions that you wrote manually on the slide.
Yes.
Can't I write this down as a variational inequality? The overall problem?
Okay, so okay, remember, it has, okay. Any equilibrium problem can always be phrased as a variational inequality problem. That's absolutely true. But the reason we like variational inequality formulations is because we have a sufficient condition for existence, right? In terms of concavity of something or other. Okay. Here, what you have to be careful about is in general. So if I just take if I just do the standard exchange economy and I write it out as a variational inequality, I do not immediately have the appeal to convexity or concavity that says that will guarantee the existence of a solution to the variational inequality problem. Okay. Now it could be, and I suspect that this is probably going to be true, that for this particular problem, if you were to write out the variational inequality, the variational inequality version of it, the sufficient condition for existence of a solution to the variational inequality will probably hold. It's not immediately obvious to me, but my intuition is that I think that would be true because of the special structure of the utility function.
Yeah. And
okay. Go ahead.
Yeah, then the question is, I mean, for variational inequalities, I have this principle of symmetry. I know that there is a convex or an optimization counterpart if and only if the Jacobian of the variational inequalities function is symmetric. So yeah. Why is this not, I mean, I'm pretty sure that this idea is too simple to be true. So why is this not the solution of the open question?
Yeah. So first, I would not make the mistake of thinking this idea is too simple to be true, and here's why. The Arrow-Debreu exchange economy with linear utilities, agents consumer choice problem does not involve this constraint that I just crossed off. Okay. in the 1970s, Bernard Cornet wrote a paper pointing out that for that instance of competitive equilibrium, there was a convex, that you could write that problem of finding that competitive equilibrium as a convex program. Okay. That paper was forgotten for 40 years. Kamal Jain, and I forget who his co-author were, stumbled upon the same convex program some 40 years later. So the answer is, it's possible that someone somewhere thought about this and it's been lost, right? Because when Cornet was writing, nobody frankly was concerned that much with computation. And you know, now we're interested in computation, and Cornet's early papers on the linear exchange economy, you know, have subsequently been discovered. Right? Okay. The stumbling block on this one, which is Hillen and Zeckhauser, first, you cannot even use the standard Arrow-Debreu, in other words, you cannot appeal to the usual Arrow-Debreu-Mackenzie argument of existence of competitive equilibrium to show that a competitive equilibrium exists in this economy. Why is that? Because in this economy, agents violate the non-satiation preference assumption. So you need a slightly different argument, right? It's this last constraint that causes problems, at least with traditional techniques. Okay. Now, if my memory serves right of this paper by Vijay Vazirani that provides some kind of fast algorithm for this, what they're making use of is they're saying, well, wait a second, checking the supply-demand condition is sort of like solving a network flow problem. So, you know, we can milk that to figure out how to adjust the prices, but you're still investing a huge amount of computational resources to find the market clearing prices. Okay, now, as far as I know, nobody has attempted to formulate this problem as a variational inequality. So I would not dissuade you from trying, because I would want you to come and tell me, the reason it doesn't work is because this annoying constraint that says you can consume at most 1 unit screws up the Jacobian in some way. Okay. But maybe it suggests some kind of Lagrangian relaxation approach where there's a price for violating that, and then you use the VI method, and then you vary the multiplier on this quantity constraint.
Okay, I'll try.
Okay. Yeah, Martin. Or the other Martin, I should say.
So since you've put me on the spot, maybe let me say 2 words about, or 2 sentences about the application that we have here. So we've started about, I don't know, 6 years ago to run Gale Shapley here for a course assignment. And we have a very large computer science department, Sven would know, and it has been grown since Sven left, actually, quite a bit. Most of the applications were assignments to seminars where each student has really unit demand, right? But we do have very large applications in the initial semesters, and I suppose that is very similar in many other European universities, at least from what I hear, where students are have to sign up to tutor groups, and tutor groups for the main courses in their curriculum, right? And they are scattered across the week, and typically students have timely preferences. And we were about to do something like run a randomized serial. And then I came across Rakesh's paper, and we said, well, this is actually an ideal application, and we actually implemented it. So to give you a bit of an idea, we are talking about 1,700 students per year that are being matched there. So we actually do this every year in the winter term. It worked quite nicely. So Rakesh has a beautiful paper on, I think, what you call bundled probabilistic serial. So the first stage would be a probabilistic serial on bundles, and then you have a randomization algorithm. And we actually put this into practice, and this has been working now since, I don't know, 3-4 years now. very successfully, I would say. So our Dean of Studies is happy, and given the large number of students that we have, it kind of coordinates. It's really kind of a distributed scheduling algorithm you can think of, where you have to fit in all these student preferences for packages of these courses into the available slots, right? So, and maybe last word, if you're interested, we do have, we have coded obviously the back end of this algorithm and some of the parts that Rakesh now didn't talk about, so the algorithmic parts. So if you're interested, we'll be happy to share this.
Let me follow up on what Martin said, because I think he's underplayed an important role that he is responsible for, which is, and which I learned from him, which is the main bottleneck with implementing, various market design algorithms for allocating scarce resources is really the user interface. In other words, getting, what's the language that you should be asking people to use to communicate their preferences? This is part of the tacit knowledge, so people recognize, yes, that's the challenge, but it's not something that we write a lot of papers about. On the other hand, nothing is going to happen unless you solve that problem, which is, it's thinking, how rich should the language be? What's the trade-off between the richness of the language and the attractiveness of the outcomes that you generate? And this is something that we have sort of heuristic sense of what's going on, but as far as I know, nothing formal.
But that is, I think, a crucial point. Also coming back to the CEI, and that was the question that I was raising, because essentially you need to. So there are some alternative procedures based on CEI, and they essentially ask students to provide utility points, and that's allowed to ask for in a way, right? So in here, for this mechanism, you still need a strict ranking over exponentially many packages, right? That's also allowed to ask for, but less so than you're asking for cardinal points, right? And I don't know how robust these mechanisms are if you have slight permutations of these cardinal points. So I think with respect to these rankings, we developed a bit of decision support tools to help students rank order their preferences, and they feel comfortable with it. But it's a subtle issue that needs to be taken care of when you want to put these things into practice, obviously.
Actually, so before we go, Sven, Martin, the other Martin, reminded me that I needed to correct myself. Correction. Earlier, when I said Cornet, I should have said Gale and Eisenberg. In other words, this problem here, the economy where agents only have budget constraints but do not have quantity constraints, that's a Gale-Eisenberg economy. And there's a Gale-Eisenberg convex program. The Cornet program that I was referring to changes this to where the budget constraint is endogenous. And that's a harder problem than Gale-Eisenberg. And the reason I was thinking of Bernard Cornet rather than Gale-Eisenberg is because another way that you can implement competitive equilibrium with equal outcomes is you take all of the goods and you say each agent, you are entitled to 1/nth share of each good. That's your endowment. Okay. Now you get the same. You get the same competitive equilibrium with equal incomes result, but now the competitive equilibrium problem that you're solving, if you ignore the quantity constraint, is the one that Cornet was looking at, and that's the reason for the confusion on my part. And I apologize to both Bernard Cornet, who is alive, and David Gale, who isn't, and Eisenberg, I forget.